Welcome. We will continue factorial experiment. Today's topic is estimation using regression approach, model adequacy in terms of test of assumptions, and sample size calculation for factorial experiments. So, in last two lectures we have talked about factorial experiments, and in last lecture I have given you the statistical analysis of factorial statistical analysis, and you have seen that when there are multiple factors, for example, two factors. So, we have computed the sources of variations A, B interaction, error, then total, and I have given you the formula for SSA, SSB, SSAB, SS error and SS total, and then the other part like ANOVA table for up to F statistics. Okay. And if you remember, the model we consider is Yij k, then this will be mu plus tau I plus beta j plus tau beta ij plus epsilon ij k, and the estimate of mu we have given as that is y triple dot bar, then tau I estimate is basically mu I cap minus mu cap, which is basically y I dot bar minus y dot triple dot bar. In the same manner, beta j cap equal to beta mu dot j cap minus mu cap, which is basically y dot j dot bar minus y triple dot bar, and then we have also computed tau beta ij cap, which is mu ij cap minus mu cap, then y ij dot bar minus y triple dot bar. No, here formula is not this, here formula is minus mu I dot bar minus mu dot j cap plus mu dot plus mu cap, and then corresponding y bar is taken, and grand mean is this. So, that means by estimation of parameters we talk about estimation for mu grand mean, estimation for tau I, estimation for beta j, estimation for tau beta ij, and also computation of residuals, which will be ijk cap. So, once we compute all those things, this is basically our Yij estimate, then in this one will be Yij k minus Yij k estimate. So, this will give you the error terms, or these are known as residuals. So, what using regression approach we will show you that how this this formula are obtained, and then we will go for plot residual plots to check the model adequacy, and finally, we will show you with how to compute sample size given the threshold mean differences or given the parameter population parameter values. So, you see that Yijk, this is our two factor factorial fixed effect model. Here we have mu, tau I, beta j, tau beta ij, these are the parameters to be estimated. So, we have one mu, A tau I, B b beta j and ab tau I beta j. So, that means we have 1 plus a plus b plus ab. So, we have how many parameters to be estimated? We have mu, that is 1 mu, plus y I j k equal to mu, plus tau I, we have I equal to 1 to a. So, a number of tau I, plus beta j, we have j equal to 1 to b. So, b number of tau b beta j, plus tau beta I j, where I equal to 1 to a, j equal to 1 to b. So, we have a b number of tau beta j, and then plus error is there y I j k. So, this will be estimated 1, these things are estimated. Okay. So, that means our number of parameters to be estimated, equal to 1 plus a plus b plus a b, and as a result there are how many equations? 1 plus a plus b plus a b normal equations. You have seen earlier that we found out SSE, which is sum of epsilon I j k square, and this will be basically triple sum of mu plus tau I plus beta j plus tau beta I j, this square, and then we have done del SSE by del mu, put 0, del SSE by del tau I equal to 0, I equal to 1 to a. Similarly, del SSE by beta j equal to 0, j equal to 1 to b, and del tau beta I j, sorry, del SSE by del tau beta I j, this will put 0, and it will be I equal to 1 to a, j equal to 1 to b. So, as a result, this one gives one equation, this gives a equation, this gives b equations, and this gives a plus a into b equations. So, total you will be having 1 plus a plus b, a b normal equations. Okay. Now, using those normal equation and the constraint, so there are certain constraints. What are those constraints? Constraint are sum total of tau I equal to 1 to a, this estimate will become 0. Similarly, j equal to 1 to b, sum total of beta j cap, this will become 0. Similarly, tau j I equal to 1 to a, tau beta I j, this cap, this will become 0, and sum total of j equal to 1 to b, tau beta I j, that also will become 0. Obviously, everywhere you please remember I equal. So, here if I put I equal to 1 to a, then j equal to here 1 to b, here I equal to 1 to a. Okay. The total into mu cap plus b n this, b n into this, plus a n into this, sum of this, plus this equal to this. Now, we have seen that sum of this is 0, sum of this beta j is 0, and this also will become 0. So, a b n mu cap will become y triple dot. So, that means mu cap will be y triple dot by a b n sample size. Similarly, here this becomes 0, and this quantity already known. So, this quantity you will calculate. So, in this manner if you go, you will calculate these values like this. So, okay. Now, what is this values? Mu cap will be y bar triple dot, tau I will cap will be y I dot dot bar minus y triple dot bar. Then your beta j cap will be y dot j dot bar minus y dot 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 bar, and tau beta, that I j, that cap will be y bar I j dot minus y I dot dot bar minus y dot j dot bar plus y triple dot bar. So, I equal to 1 to A, j equal to 1 to B. So, this is what is the parameter estimation using regression approach. Okay. So, as I told you in the first, I started with this, I told this one that y I I dot bar minus this, okay. The same thing, these equation what we have written here, these equations using the regression approach, we are also getting the same equations. Okay. Now, I will show you one example and how do we compute all those parameters as well as their errors. So, this is what is the example which we have discussed earlier. Here basically shelf life is a response variable, pressure with 3 levels, temperature with 3 levels, controllable variables, 4 replicates in each experimental setting, and then these are the data, hypothetical data we obtain. Now, using this data set and the formula what we have discussed here in regression approach, these formulas, using these formulas with the data set, we will be in a position to compute all the parameters for this 2 factorial experiments. Now, see what happened here. This rod experimental data you know. What we have done here, we have created row total, row average, row treatment, column total, column average, column treatment. Okay. So, row total you see, ultimately you see the data set here. Data set here, row with respect to low, with respect to medium, with respect to high, column with respect to low, respect to medium, respect to high for temperature. Then row total for low will be total of 1, 2, 3, 4 into 3, 12 observations. Similarly, column total will be for another 12 observations. So, we have computed here. So, 30 plus 55 plus 26 plus 80, this is what is the cell total, which is 191. Second cell total is 119, third cell total is 110. You sum up 191, 119 and 130, 110, what you will get? You will get 420. So, that means this 420 is sum of all the values related to pressure low. Similarly, second one is sum of all the values related to pressure medium, all the values related to pressure high. So, these are all row total. Now, row total 420 divided by 12, because there are 12 observation, will give you 35. So, then 35 is the row average for when. So, that means what happened? Okay, I will come back later on. Then similarly, you find out the column total. Column total will be this cell total plus this cell total. So, 191 plus 223 plus 176, this will be 590. Similarly, here 119 plus 79 plus 183, this is 381, and then 110, 142 and 70, 322. So, essentially what happened? You have pressure low, medium and high, this is pressure. Then we have temperature also, temperature is our low, then our medium, then high. Okay. So, this is temperature. Now, what I said that we are computing here we are computing row total. For the first row, this one is 420. For the second row, this is 444. For the third row, 429. Similarly, we got column total. Column total is here we got 590, then 381, then 322. Then what is the grand total? Grand total is sum of rows total or sum of column total. This is 1293. So, in addition, we have computed cell total, means there are 4 observations, one the total of that 4, total of these 4, total of these 4, like this. So, cell totals are here it is 191, then here it is 119 and here it is 110. And similarly, here the second one cell total is 223, 223, then your 79, then your 142, and third one is 176, then 183, then your 70. So, 191, 223 plus 176, this 3 plus 1 4 plus 6 10. This total gives you this total gives you this total gives you this total gives you this, like this. So, first you calculate row total. This row total is y I double dot, that is what is row total. Similarly, column total is nothing but y dot j dot, this is our column total. Then what I am saying, you find out row average y bar I double dot. So, this is your row average. So, how do you compute the row average? Similarly, find out row column average, this equal to column average. So, how do you find out? So, row total divided by number of observation will be 12. So, this will give you 420 divided by 12 will give you 35. 444 by 12 will give you 37. Then your 429 by 35 will 12 will give you 35.75. Similarly, column average you will find out 590 by 12 is 49.7, then 31.75, then your 26.83. Then you find out the grand average. Grand average means 1293 divided by 36, because you have A equal to 3, B equal to 3, N equal to 4. So, A, B, N equal to 36. All total is to this divided by 36, this will give you 35.92. So, from parameter estimation point of view, this one is your y triple dot bar, which is an estimate of mu cap. Now, what happened? We try to find out row effect. Row effect means what? That is basically tau I cap. Okay. So, similarly, find out the column effect. This is nothing but beta j dot beta j cap. Okay. So, your tau I cap will be what? That is mu I cap minus mu cap. Mu I cap minus mu cap. It is nothing but mu I cap is this one minus mu cap is this one. So, this is basically y I t triple double dot bar minus y triple dot bar. So, in that sense what will happen 35 minus 35.92. So, this will be minus 0.92. Similarly, 37 minus this will be 1.08. Similarly, then the other one will be 0.16. So, these are the treatment effect for pressure. In the same manner, if you subtract the column average from the grand average, what you are getting? Here you are getting 13.25, here you are getting minus 4.17 and here you are getting minus 9.08. These are nothing but the beta j cap, that is temperature effect. Interestingly, if you sum up this tau I, this plus this, sum will give you equal to 0. Here also if you sum up, this will give you 0. So, that is the restriction. So, from parameter estimation point of view, mu cap is known now, that is your 35.92, then tau I cap 4 values are known, 3 values are known, minus 0.92, 1.08, minus 1.16. So, this is what is tau I, and beta j cap point of view, you have 13.25 minus 4.17 minus 9.08. What more you want? You want tau beta cap I j. So, what is this computation? This will be y I j dot bar minus y I triple double dot bar minus y dot j dot bar plus y triple dot bar. It indicates that what is y I j bar? You have to, how many observations are there in each of the cell? 4 observation. This is the total divided by 4, this total divided by 4, this total divided by 4. So, every total divided by 4 will give you the cell average. Now, this minus row average minus column average plus grand average will give you, that means tau beta cap 1 then it will be y 1 dot bar minus y 1 dot bar minus y 1 dot bar plus y dot bar. So, this will be 191 by 4 minus 35 minus 49.7 plus 35.92. This will give you a value called minus 0.50. In the same manner you compute other values. Now, see the slide. So, we have these are the treatment of row treatment pressure effect, column treatment temperature effect, and these are the cell treatment effect, interaction effects. So, there will be how many interaction effects? 3 cross 3 9, 1 2 3 4 5 6 7 8 9. Now, you sum up across rows, this plus this will be 0, across column this plus this will be 0, these are the constants are satisfied. So, this is what is your parameter estimation in 2 factorial design with different levels. Okay. Now, what will be your predicted value? Predicted value will be, you just see, predicted value will be nothing but the cell average. Cell average will be the predicted value, because if you see that the formula, so y I j k equal to mu plus tau I plus beta j, so tau beta I j plus epsilon I j k. This is what is the predicted value. Now, if you put this, suppose y triple dot bar plus this one y I double dot bar minus y triple dot bar plus y dot j dot bar minus y triple dot bar plus you put y I j dot bar minus y I dot bar minus y dot j dot bar plus I dot bar, this one, then plus error plus epsilon I j k. So, this one, this will be cancelled out, this and this will be cancelled out, this and this will be cancelled out, cancelled out, 1 y I dot bar, this and this will be cancelled out, sorry, this is y dot j dot bar. So, that means y dot j dot bar, this will be cancelled out, and this is cancelled with this, but this one will be cancelled out with this. So, it will be remaining like this. So, y I j dot bar plus epsilon I j k, and this is what is our y I j k predicted value plus error y I j k. So, this is nothing but the cell average. So, all cell averages are put here. So, when observation, so these are there will be 36 observations, and you are getting y value and y predicted value, residuals you are getting. This is what is the computation of residuals. Okay. Now, next is our adequacy test. In adequacy test, we will show you the residual plots. First one is the QQ plot, quantile plot. You all know what you do basically, you write down the errors from in ascending order. So, there will be 36 errors. So, you write down from ascending order, mean suppose error, if I say error, if I write that residuals is E I and ascending order this, and then you 36 is this one, and then you find out I minus 0.5 by n, here n equal to 36, then you will be getting cumulative probability, and then find out the corresponding z value, assuming that errors are normally distributed. Now, plot these two. So, z value and residuals. So, this is what it is plot here, and we found that there is a fit line, straight line fitting to the origin. So, it is basically it is normally data normally distributed. Similarly, plot of residuals, you see the residual versus y predicted. So, you have the y predicted value, you have the residual values. So, you plot residual y predicted, there is no pattern. So, it gives us many things. For example, that basically talk about that that data independent and those kind of things are, it is this one is done. Okay. So, now here if I go for residual with individual that x values. So, it will give you that across x whether the residual is showing a constant variance or not. So, from the plot here we cannot say that there is a change in variability of residual across pressure, but in case of across temperature there is little change, but maybe that change is not that much significant change maybe, but you require some other kind of test to check whether there is the violation of homoscedasticity here or not, but from the plot there is slight difference. Then another important thing is that sample size calculation. So, in like one way ANOVA we have given you the sample size calculation when there are two issues, when if you know the tau I beta j and tau beta I j, these values are known, then you will use one kind of formula. If the values are not known, then you have to and the difference between two treatments or two means are given, either row means or column means, or the interaction effects, the difference given, then you will be using another kind of formula. First, I will let us see that if we consider that the difference between any two row means is d, then the phi square will be computed like this. What is this phi square? N b d square by 2a sigma square. Now, if the difference between any column means is d, then it will be n a d square by 2 b sigma square, and if it is any two treatment difference of any two interaction effect is d, then the minimum value of phi square will be n d square by 2 sigma square into a minus 1 b minus 1 plus 1. This is what is the results obtained from statistical theory. Okay. So, then once we know phi square, we know the phi, then we know the what is the sample your degrees of freedom, numerator denominator degrees of freedom, and then using the OC curve we will be able to find out the beta value. For example, if you choose a particular alpha and know the beta phi value, and then knowing the degrees of freedom nu 1 and nu 2, you will be knowing that what is the probability of accepting a false hypothesis, that is beta, that can be computed. So, in this table we have given the suppose the tau I beta j and tau beta j, these population values, parameter values are known. In that case, you use this formulation and use the chart also, but it is hardly known because it is difficult to know. From the data what we know, that we know the estimate of this, and then we will choose a particular difference. Now, in this example I will show you only the suppose if you go back to the parameter estimates, you see the treatment effects, temperature treatment effects are very large, and also you have seen in the two factor analysis of variance the temperature effect is significant. So, we are now you finding out the that this one the sample size we in example considering the temperature level and its levels. So, suppose 40 hour, that means that if the difference between mean life of a perishable product for between two temperatures is this 40 hours is the acceptable one, and if we assume that the standard deviation is 25. Okay, so, this is not from the data we have computed the standard deviation, we have assumed that it is 25, let it be, it may not be. So, if this is the situation, then phi square equal to this, and then putting a, b and d value, sigma square value, it will be 1.28 n, and then for different values of n, you compute the phi square value and then phi value, and you know the degrees of freedom, all those all cases basically that degrees of numerator degrees of freedom and denominator degrees of freedom. So, all those cases you will be computing once you know the a n values and these values are b values are known. So, now if numerator degree of freedom is 2, denominator okay, this one is numerator, another denominator degree of freedom is 9, that is nu 1 and nu 2, and then using your phi, phi is 160, and then you have to use appropriate one here 2, 3 and different values of nu 2 is given. So, this plot will not help you, you require nu 1 equal to 2 and nu 2 equal to 9, that plot then you will find out that the beta value is only 0.45. Similar thing we have given in one way analysis of variance when you talk about sample size calculation. Okay. So, you require 2 degrees of freedom, that is nu 1 and nu 2, and you require phi, and then you will be able to find out the beta value. This beta value is computed here. Okay. So, if we consider that beta one power should be 90% or more, or beta values at max may be 0.1, in that case you require 4 sample size should be 4, then you will be getting the desired level of beta value. In this example we have chosen for replication is 4, in this example replication is 4. Okay. So, this is what is your sample size calculation. Only one mistake here is that we talk about both case numerator, one is this is numerator, this is denominator, or nu 1 and nu 2 first degrees of freedom and second degrees of freedom you just write down. And second thing is that this is the sigma square, we have assumed that 25 and it may not be 25. So, if actual values are known, then this calculation will be different. Okay. And you have to, once you know the nu 1 and nu 2 numerator and denominator degrees of freedom, then and you know the phi, then you have to find out the alpha value. Alpha will be usually 0.05 or 0.01. If you took alpha equal to 0.005 and phi value is given like, and phi values are known, and if the nu 1 and nu 2 matches, then from there you will be able to find out the beta values. Okay. So, this is what is our sample size calculation, and I hope that you will be able to find out the sample sizes. So, very quickly I will just recall all the things what is taught in this lecture now, that we first told you the estimation part, and estimation means basically the parameter estimation. Now, what are those parameters? Mu, tau I, beta j, tau beta I j, and I have given you how from the experimental data you will compute all those things, and then the predicted value of every observation, or other way I can say the what will be the fitted values, and then from fitted values when you subtract it from the original value you will get the residuals. This is what first thing we have given to you, and you have with an example we have shown how this computation will be done. And also what we have seen that these formula, that calculation estimation of mu, tau I, beta j, tau beta j, all those things using the regression approach by that minimizing the sum square errors, how it is to be computed, that is also shown. Please remember, the number of parameters to be estimated is equal to the number of normal equations, or number of normal equations you will be using will be equal to the number of parameters to be estimated. There will be lot of constant depending on the what kind of factor model, it is 2 factor factorial model or 3 or more, but the procedure remains same. There will be lot of constant which is to be satisfied. Putting all those things you will be able to estimate the parameters. After you estimate the parameters, then the sample model adequacy test in terms of normality, in terms of homoscedasticity, in terms of independence or uncorrelated errors, all those things you require to be satisfied, required to be tested, and you see that they are satisfied or not. And finally, sample size is very important, and so what I want that you use the OC curve concept what we have discussed here for sample size computation. So, thank you very much.